Enthalpy of the solution can be calculated by enthalpy of lattice plus enthalpy of hybridization. Change in enthalpy when 1 mole of the solid substance gets converted into another state or liquid state, that is known as standard enthalpy of fusion. Change in entropy is given by delta S is equal to S2 minus S1 for entropy at final stage minus entropy at initial stage. Hello everyone, I am Vidhyaashram Prasad, Department of Chemistry, Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. Okay, today I am going with Thermodynamics session 3. Let us study today enthalpy of solution, lattice enthalpy, change in enthalpy during phase transformation, Hess law and its importance, spontaneity, entropy, change in entropy during spontaneous process, as well as Gibbs free energy and relationship between standard free energy change and equilibrium constant. Okay, let us go with the first topic, enthalpy of the solution. Here, enthalpy of the solution means it's a change in enthalpy. It's a change in enthalpy of the substance when 1 mole of the substance, is dissolved in specified amount of solvent. It is dissolved in always specified amount of solvent. Let us take one example. Here, let us take today sodium hydroxide and it is dissolved in water molecule. Okay. Then here, let us take, they have said amount of solvent. Solvent means here we have to take water molecule. Okay. If you take 1 gram of sodium hydroxide, which is in the solid state, for that if you should add around 10 ml of water molecules. We have to add 10 ml of solvent. Here solvent is water molecule. Okay. So then only it gets dissolved. If you add little amount of solvent, what will happen? It does not get dissolved. Did you understand? So we can say that it's the enthalpy of the solution when 1 mole of the substance is dissolved in particular solvent. Okay. Next thing is enthalpy of the solution. Enthalpy of the solution, how you will calculate, which is in the solution means always we should know that it will be in the liquid state. We should know that it is always should be in the liquid state. Okay. Here enthalpy of the solution can be calculated by enthalpy of lattice plus enthalpy of hybridization. Enthalpy of lattice plus enthalpy of hybridization. Okay. Next, let us calculate when enthalpy of the solution will be positive. It is positive only when the process is endothermic. Okay. Next thing is lattice enthalpy. What do you mean by lattice enthalpy? It is a change in enthalpy. It's a change in enthalpy when 1 mole of the ionic compound, dissociates into gaseous state. It dissociates into ions and it will be in the gaseous state. Did you understand? Here you see sodium chloride ions, Na plus Cl minus ions are there and it has been converted into, directly it has been converted into gaseous state. How much energy is required? 788 kilojoules per mole. Here directly solid state to gaseous state. Here directly it has been converted from solid state to gaseous state. So that is known as lattice enthalpy. Here let us study today. Let us take sodium which is in the solid state. Okay. Then let us convert it into the gaseous state. Okay. Here you have been converted into gaseous state. Okay. After that, we have to remove 1 electrons from the sodium which is in the gaseous state. Okay. Here we have to remove the 1 electron from the sodium atom when it is in the gaseous state. So that is known as sodium ion. So sodium ion, that energy is known as ionization energy. Okay. Next one is chloride molecule which is in the gaseous state. Next you have to bring that chloride molecule to chlorine atom. That is known as dissociation energy. How much energy you should require? You require 122 kilojoules. Okay. After that, from chlorine atom, you need to supply little amount of 1 electron to the chlorine atom. What will happen? It will be converted into chloride which is in the gaseous state. Okay. Now let us combine sodium which is in the gaseous state and chloride ion which is in the gaseous state. You will get sodium chloride which is in the solid state. When you combine both, What will happen? It will be in the gaseous state. After some time, let us freeze that molecule which is in the gaseous state. You will get purest form of sodium chloride. Okay, that energy you need some amount of energy, right, to bring the two ions which is in the gaseous state to solid state. That is known as lattice enthalpy. U is equal to minus 788 kilojoules. Okay, next thing let us study change in transformation. Here, phase transformation. Phase transformation means what? Change in enthalpy during phase transformation. They have said change in enthalpy during phase transformation. Here let us study standard enthalpy. Standard enthalpy. Standard enthalpy means what? It's a change in enthalpy when 1 mole of the solid substance it has been converted into liquid state. It's a change in enthalpy when 1 mole of the solid substance gets converted into another state or liquid state. That is known as standard enthalpy of fusion. Here always chemical substance will be in the solid state. It has been converted into liquid state. Okay. Here next one is standard enthalpy of sublimation. Sublimation means what? You have taken one substance which is in the solid state, you are directly converting it into gaseous state. Means it's the amount of enthalpy or change in enthalpy when 1 mole of the solid substance, sublimes at constant temperature. Sublimes at constant temperature. So that is known as when it is solid to gaseous state. Then we should say that change in enthalpy for sublimation. When you are converting solid substance to gaseous substance, then we have to say that it's a change in enthalpy for sublimation. Okay. Next thing is standard enthalpy of fusion. What do you mean by fusion? Here also fusion we learnt, here also fusion we have learnt. But here we are converting solid substance to liquid state. Did you understand? So we can say it standard enthalpy of fusion for the chemical when it is in the solid state. Now let us take standard enthalpy of fusion when the chemical is at liquid state. Now you are converting liquid to gaseous form. Directly you are converting. Did you understand? So how much amount of enthalpy will be required to change a molecule when the substance is at liquid state to gaseous state? So that is known as standard enthalpy of fusion for the chemical when it is in the liquid state. Here how much energy you need to supply? That one we should know, right? So we should calculate here. So for water molecule from liquid state to vapor state, it requires 40.7 kilojoules per mole. Okay. Next thing is Hess law. What do you mean by Hess law? It's a change in enthalpy. It's a change in enthalpy. Standard condition we should know. For the chemical reaction we should know all the standard condition. But it's a change in enthalpy, change in the sum of standard molar enthalpy of formation of products minus the corresponding sum of the reactants. We should know that here you are calculating the change in enthalpy for some chemical reactions. For some chemical reaction, we are calculating how much enthalpy is required. Then how you will come to know that? First we have to take the enthalpy of products minus it's a enthalpy of reactants. Okay. Next thing is let us take importance of Hess law. Here what is the importance of this Hess law? Here for some particular chemical reaction it cannot be performed in the laboratory. Hess law cannot be applied when you does not perform a chemical reaction in a laboratory. Did you understand? For some chemical reaction cannot be performed in the laboratory, correct, right? We have to perform in an open space. Okay. Then Hess law cannot be applied. Okay. Next thing is the reaction rate is very slow. The reaction rate is very slow. Third thing is reaction may involve the formation of solid products or side products. Side products. Here why we are saying the side products? Because when you are doing the reactions at open environment, not in the laboratory, because here Hess law cannot be applied for the laboratory reactions. It can be applied only in the presence of open environment. When you are doing the reactions at open environment, your chemical substances may absorb the temperature or any other gases from the atmosphere. So we may obtain some impurities when we are doing the chemical reactions. Okay, here, but enthalpy change for such reactions can be determined by applying the Hess law. You should know that always when you are performing the reactions at open environment, Hess law can be applied, but you may get side products because all type of gases will be there in the open environment. Okay, next thing is example. We have to find right now one example. Let us see now. Let us take carbon content material, because in open environment carbon content is there, but we cannot find the enthalpy, correct, right? So we are taking the chemical substance which contains carbon. Did you understand? Here graphite which contains carbon, it reacts with oxygen to form carbon monoxide. Now we have to find the enthalpy. Okay, however, it can be found for some other reactions by taking related species. So I have taken today related species. Okay, today let us take one reaction, carbon which graphite which contains carbon, and it is treated with oxygen. We obtain carbon dioxide. So delta H will be 393.5 kilojoules per mole. Okay, again let us take one carbon monoxide which is present in our environment, and it is treated with oxygen, open atmosphere. What will happen? We obtain a carbon dioxide gas. So what is the enthalpy? 283.0 kilojoules per mole. Okay, however, we can combine the above two reaction. When we are combining above two reaction, what we will get? First we got carbon dioxide, second time also we got carbon dioxide only. So let us take that carbon dioxide, and it is kept in the open environment. What you will get? You will get carbon monoxide plus oxygen you will get, because you are exposed this chemical reaction to the open atmosphere. So we will get carbon monoxide as well as oxygen. Our aim is to get only carbon monoxide. Did you understand? So from equation 1 and equation 3, this is the equation 1 and this is the equation 3. When you combine these two equations, you will get how much amount of carbon monoxide present in particular material, and we can find the enthalpy of that reaction. How much enthalpy is required for the formation of carbon monoxide? We will come to know by taking a related species which contains carbon. Okay, so how much we got? Minus 393.5 kilojoules per mole. Okay, next thing is spontaneity. What do you mean by spontaneity? Spontaneity means it's a process which takes place of its own without any external help or external aid. For example, flowing of water from higher level to lower level. This is an example for spontaneity as a process. Why it is called a spontaneous process? Because it takes place of its own. Flowing of water from higher level to lower level, but it does not take place from lower level to higher level. Okay, so we can say that for spontaneous process, we can say example is waterfalls, flowing of water from higher level to lower level. Okay, next thing is non-spontaneous process. For non-spontaneous process, we can say that process which takes place with the help of external aid. Example is pumping of water. Pumping of water from sump to overhead tank. This is an example for non-spontaneous process, because we are pumping the water from sump to overhead tank with the help of some pressure and by using pump. Here pressure is applied in the terms of pump. Did you understand? So we can say that it is a non-spontaneous process. Okay. Next thing is entropy. What do you mean by entropy? It is a measure of randomness. It's a measure of randomness in a system. It's a measure of randomness in a system, and it is denoted by S. Example is melting of ice. At particular temperature, it will react with an open environment, right? So we can say that it's a melting of ice. Okay. Next thing is change in entropy. How change in entropy takes place during spontaneous process. Okay. Let us take melting of ice at room temperature. Melting of ice at room temperature. So let us take S1 is the initial entropy. When you are taken ice from the refrigerator, what will happen? It will have some entropy, but it will have very less. Did you understand? So let S1 be the initial entropy and S2 be the final entropy. S2 be the final entropy after it has been reacted with open environment. Did you understand? So S2 be the final entropy. So change in entropy is given by delta S is equal to S2 minus S1 for in entropy at final stage minus entropy at initial stage. Okay. Next thing is, let us calculate the how entropy takes place during a spontaneous process and what happens when the temperature increases or decreases, that and all. Let us study here. Here entropy increases when temperature always increases. Okay. Next, entropy of the system is a state function. It depends upon the initial state and the final state, but it does not depends upon the how the process has been takes place. Okay. Here it depends upon the initial state as well as the final state, but it does not depends upon the how the process has been gone. Okay. So change in entropy is given by delta S is equal to entropy at final stage minus entropy at initial stage. Okay. Next thing is when heat is absorbed by the system. So we should calculate, right? There will be change in entropy when heat is absorbed by the system. So delta S is equal to Q by T. Here Q is the heat absorbed and T is the temperature. Okay. Next thing is, note how you will calculate for a spontaneous process. How you will calculate change in entropy for spontaneous process. How you will calculate? Just delta total entropy is equal to system plus surrounding. System plus surrounding, and it will be always greater than 0. It will be always greater than 0. Okay. Next thing is, when the system is at equilibrium, change in entropy will be always equal to 0. Change in entropy will be always equal to 0. Okay. Next thing is Gibbs free energy. What do you mean by Gibbs free energy? It's a maximum amount of energy. It's a maximum amount of energy available for a system during a process that can be converted into useful work between initial state and equilibrium state. Initial state and equilibrium state means it's a how much amount of energy. It's a how much amount of energy you should supply. You should know, right? Means you need to convert from one form to another form. But how much energy you need to supply, you should know. Then only you can convert from one form to another form. So that energy is known as Gibbs free energy. Okay. Here Gibbs free energy can be calculated by G is equal to H minus Ts. Here this equation is called Gibbs free energy and it depends upon the path of the process. Entropy does not depend upon the path of the process, but Gibbs free energy depends upon the path of the process. Okay. Now let us calculate change in Gibbs free energy. How you will calculate change in Gibbs free energy? Delta G is equal to delta H minus T delta S. Delta H minus T delta S. Here this equation is called Gibbs equation for the free energy change. Okay. Now let us calculate Gibbs free energy for spontaneous, non-spontaneous and equilibrium. For spontaneous process, delta G will be always negative. For non-spontaneous, delta G will be always positive. For equilibrium, delta G will be equal to 0. Okay. Next thing, let us study Gibbs free energy for which one? Feasibility of the reaction we should know. Okay. Now let us take for the exothermic process. Feasibility of the reaction, how the process is carried out and particular conditions will be there, right? So we have to calculate the Gibbs free energy. Okay. Now let us take for the exothermic process. For exothermic process, delta H is always negative. Delta H is always negative and delta S is always positive and delta G will be negative. Delta G will be always negative for spontaneous process. Okay. Always negative for spontaneous process. Next, for if delta S is negative. Now first we have taken delta S is positive. Next let us take delta S is negative. If you take delta S is negative, what will happen? temperature will be low, and temperature is always less than delta H, and delta G will be always negative, and this process is known as spontaneous process. If the temperature is very high, now let us increase the temperature, then T delta S will be greater than delta H, and delta G is always positive. Delta G is always positive. Then, and this process is known as non-spontaneous process, and this process is known as non-spontaneous process. Okay. Now let us study for endothermic process. In endothermic process, delta H is positive. Delta H is positive. Now let us take if delta S is positive. If delta S is positive and temperature is low, delta S is positive and temperature is low, what will happen? T delta S is less than delta H, and delta G will be always positive. Okay. Now let us take if temperature is high. Now let us increase the temperature. Then T delta S will be greater than delta H, and delta G will be negative. Delta G will be always negative, and this process is known as spontaneous process. Okay. If endothermic process, if the endothermic process is not a spontaneous process, now let us take one reaction and it is not a spontaneous reaction. You have to make it is a spontaneous. What you have to do? Let us increase the temperature. Let us increase the temperature. Then what will happen? It becomes spontaneous. It becomes spontaneous. Okay. And now let us take delta S is negative. Now delta S is negative means delta G is positive. Delta G is positive, and this process is known as non-spontaneous process. Okay. And when delta H will be equal to T delta S, when delta H will be equal to T delta S, then delta G will be equal to 0, and this process is known as equilibrium, and this process is known as equilibrium. Now let us take the relationship between standard free energy change and equilibrium constant. Okay. Now let us take one equation. Okay. We know that delta G will be equal to delta G naught plus products divided by reactants. We know this. Okay. Now let us substitute this formula for above equation. Okay. So delta G will be equal to delta G naught plus products. Here this is the product. Products divided by reactants, we know that. Okay. We know that products divided by reactant. This is a reactant side and this is a product side. Now let us take delta G naught will be equal to 0 at equilibrium. At equilibrium, delta G naught will be equal to 0. Then delta G will be equal to this is the relationship between standard free energy change and equilibrium constant. This is all about the thermodynamics. Okay. And in this chapter, we have got Born-Haber cycle or lattice enthalpy. We can say Born-Haber cycle or lattice enthalpy, and derive the expression for work done in terms of adiabatic process, and write the relationship between Cp minus Cv is equal to R. These are all some important questions in thermodynamics chapter. Thank you. This is all about in thermodynamics.